Okay, good morning, everybody. So we had a little bit of snow to get through today, but I see most people got here. Okay, so last class, we talked a little bit about the carbonyl group. The important thing to remember for the carbonyl group is to be able to take a look at it and make an assessment as to its reactivity. We talked about this carbon being electrophilic. That is, it has a partial positive charge because of the electronegativity of the oxygen that it's bonded to. And it's susceptible to reactions with nucleophiles. And nucleophiles, typically, we think of nucleophiles as something they may be charged or uncharged, but they have a pair of electrons that are available to form a bond. And we draw our curly arrows to indicate that these electrons can reorganize and form a bond between that nucleophile and the carbonyl carbon. And we typically will promote a pair of electrons up to the oxygen, and we get this thing. Okay, so that's kind of the central theme that we're going to want to think about in terms of the reactivity of the carbonyl group that we'll be discussing over the next little while. Now, what can this thing do is the next question. Once we form it, what we're going to spend the next couple of weeks looking at is what can then happen to that thing. One thing that's fairly common is often we do these reactions and we have some source of a proton, might be water, might be something else, and we protonate it, okay? So that's one of the themes that we're going to see today. We'll have a carbonyl group, we'll react it with something. We're going to talk about oxidation reduction reactions. We're going to be reducing the carbonyl group later today, okay? But what can this thing do is going to be a central question you're always going to ask once you get here. If there's not water, one of the things you always have to remember these things can do is go backwards, okay? So what we want to do now is just, we started off talking about, or we ended last semester talking about alcohols, and now how can we interconvert alcohols and carbonyl compounds? It's really just an oxidation reduction reaction, and we want to take a little bit, what do we mean when we talk about oxidation and reduction in an organic sense? So if we have some compound, we'll start off relatively easy with some alkane, and we can oxidize this alkane, and you'll often see this as just saying it's an oxidation. We can oxidize that alkene by adding oxygen to it. It's not really the oxygen content increases, that's clearly an oxidation. It's not clear that this is an oxidation, but it is, and that is when we, in this case, we didn't add any oxidation to it, but we did do an oxidation reaction. We actually removed hydrogen. And we'll see when we go back, an oxidation can be thought of as increasing the oxygen content or reducing, I shouldn't use reducing actually, taking away some of the hydrogen content. And in this case, we've lost two hydrogens on going from this alcohol to this aldehyde. We lost one of the hydrogens on the carbon and one of the hydrogens on the oxygen. We can further oxidize this to get a carboxylic acid. In this case, it's fairly obvious that it's an oxidation because we've added some oxygen. Now we can go in the reverse direction as well, and we talk about reducing. And in organic chemistry, you will often see this type of box indicating that we've done a reduction. So a reduction, we can remove some of the oxygen. So oxidation is going this way. We put oxygen, more oxygen in, that's an oxidation. We can remove an oxygen. In this case, we've just removed an oxygen, so we've done a reduction. It's not clear why we have this H there. But another way of thinking in organic chemistry, and not other types of chemistry, we often talk about a reduction as being the addition of hydrogen to organic molecules is a reduction reaction. And we'll talk a little bit about that later, why it's a reduction reaction in organic chemistry. We'll talk about that today. But at some point I'll talk about why it's not necessarily a reduction reaction in other types of reactions. So we want to be aware that we're oxidizing compounds coming this way, we're reducing compounds going the other way. But now I want to talk a little bit about oxidation and reduction in organic molecules. Okay, so here's another example of an oxidation reaction, and it's not really obvious why this may be termed an oxidation reaction. I'll show you the reaction and then we'll talk about why. So what reaction do we want to do? Okay, well, we can have some compound RCH3, and we do some reaction where we're going to replace one of those hydrogens with a halogen. We'll talk about this as being an oxidation reaction, and this will be, when we talk in just a second about oxidation numbers, this will confuse us a little bit. The reason we talk about this as being an oxidation reaction is because we've replaced a hydrogen with a more electronegative atom. So that's why we talk about it as being an oxidation number. What about if we, an oxidation reaction, sorry. What about if we use oxidation numbers? How can we talk about the oxidation number of carbon? Remember your rules for determining oxidation numbers from first year. Hydrogen was always +1. Oxygen was always -2 unless it was a peroxide. Oh, there was an exception. Hydrogen was always +1 unless it was a metal hydride. What was it then? Does anybody remember? It's -1. Okay, so if hydrogen is +1, whatever it's bonded to has to be -1 if the compound is neutral, or it has to add up to the charge. So in this particular compound, CH4, what's the oxidation state, if you will, of carbon? Well, if each of the hydrogens is going to be +1, the carbon oxidation number is -4. What happens now to the oxidation number for the carbon here? Now, if you go back to your first year rules, you decided that oxygen was -2, and it's bonded to a hydrogen here, so the other minus must be on the carbon. Okay? What we're going to do in organic chemistry is a little bit different. We're just going to count the bonds, and we're going to say each of these hydrogens is +1, so for every carbon hydrogen, the carbon must be a -1. For every carbon oxygen, we add 1. So for this one, we go from, our carbon is now 1, 2, 3, -3, but we have to add 1 here. The oxidation state for our carbon is -2. Now here's, anybody able to figure out the oxidation number for the carbon in this molecule? It is 0, okay? So what we're finding out, what we're doing is when carbon is bonded to hydrogen, the hydrogen has to be a +1, so it's going to be a add a minus. It's going to subtract 1 from the carbon. The oxygen, every bond to oxygen will be a +1 on the carbon, okay? Because the oxygen, so here we have our carbon is -2 because of the hydrogens, and there's 2 bonds to the oxygen, so we have to take -2 and add to that 2 for the 2 bonds to carbon, and it's 0. And then finally we have this compound. What's the oxidation number there? So that makes it -1, that makes it 0, that makes it 1, 2, so it's +2. So the highest oxidation number we can have for carbon then I'll put it up here. What's our oxidation number for that carbon? +4. Okay, so carbon goes from -4 to +4. What about our compound up there? How do we figure out? So I said that CH4 to give me CH3Cl. Let's draw it like this. What would the oxidation number for that carbon be? So that's right, -2. Okay. Why -2? What was your?
Oxygen's more electronegative than carbon, and chlorine is also more electronegative than carbon. So.
Right. Oh, actually, I'm sorry. Oh yeah, that's right. You're right. So our hydrogen is less electronegative than carbon. So each of those is a plus, so it's -3 for the hydrogens, but chlorine is more electronegative, so we give it a -1. If you remember your oxidation rules, the halogens were always -1, so that's -2. So we can see that we've oxidized our carbon. We've gone from -4 to -2. So the way we do count things up is carbon to hydrogen. We always, on carbon, -1, okay? If we have a carbon-carbon bond, it doesn't change because obviously carbon and carbon have the same electronegativity. And carbon to anything if X is more electronegative than carbon, we add 1 for every CX bond to the carbon. Okay? Now we're going to actually change this. This could actually be H or any atom less electronegative than carbon. Let's just, so that's the rule here. For any atom that's less electronegative than carbon, our carbon, we subtract 1. If we put something that's more electronegative than carbon, we add 1. Okay, so let's take a look at something like Now, it gets a little silly because in actual fact, if we did the oxidation numbers of each of these carbons, what's the oxidation number in this carbon? It's got 3 hydrogens and 1 carbon. So 0 for the carbon and -1 for each. So it's -3. This one has 1 bond to carbon, 3 bonds to carbon. Each of those is 0 and only 1 bond to hydrogen. So it's -1 and -2. If we did a reaction where we add hydrogen to the double bond, we reduce that. We talk about reducing that double bond, and the reason we say it's reduced is because now if we take a look, this remains the same. Each of these carbons, its oxidation number has been reduced by 1. Okay? So that's why we talk about the addition of hydrogen to organic molecules as being a reduction. Okay? So you want to get used to that. You'll hear it all the time. You'll hear all the time about how we reduce the carbon-carbon double bond. That typically means we added hydrogen to the carbon-carbon double bond. We can reduce okay? Here our carbon goes from 0 to -2. So it's been reduced as well. We've reduced this carbon-oxygen double bond. We talk about reducing the carbon in this case. Okay, so that's why the addition of hydrogen in organic chemistry is talked about as a reduction. So up there we reduced a carbonyl compound. And we can use that strategy to make alcohols from carbonyl compounds. So if we have some carbonyl compound, and I'm just going to call it, I'm just going to use R, we can reduce. And again, we use our generic H in a box. That means we're reducing it. And this gives us a primary alcohol. Am I writing large enough? Is that too small in the back of the room? Anybody? Can you read that? Okay. If I happen to start writing small, just let me know. I'll try and write bigger. Now, as it turns out, we can also reduce. This is an aldehyde. This is a ketone. We can reduce this as well. And we get a secondary alcohol. Okay? We can reduce other carbonyl-containing compounds. In fact, we can reduce this thing. And I'm going to call this R prime. So these two may or may not be the same. This is an ester. It's actually formed by reaction of a carboxylic acid with an alcohol. We can reduce these. What do you suppose our products are? Our products are actually, we get this compound that comes from this section of the molecule, okay? And we get another compound, R prime, OH. Notice this is our CH2. That is the former carbonyl carbon right there when we do the reduction. I'm going to put it in a little box. So in our notes we realize that that carbon there came from the carbonyl carbon. This alcohol, we don't know what it is. It could be primary, secondary, tertiary alcohol, but it came from this portion of the molecule. Okay? We can also reduce carboxylic acids, and they give us, now I'm going to write it, they also give us a primary alcohol. In this reduction, what do you suppose the other product is from this reduction? It's just going to be water in this case, okay? So, as it turns out, aldehydes are relatively easy to reduce, and so are ketones. Esters and carboxylic acids are tougher to reduce. They require tougher conditions. So, I'm going to talk a little bit about a couple of reducing agents that we can use. One that we use a lot, but you guys won't use in the lab, is something called lithium aluminum hydride. Okay, sometimes you'll see that called LAH, which is really lazy because we can draw out the whole. That's the formula for lithium aluminum hydride. What do we know about whenever we see sodium and potassium in any kind of chemical compound? What's the charge on the sodium or the potassium? It's +1. We rarely see neutral sodium or potassium. The same is true for lithium, okay? So this compound is actually a salt. It's lithium salt, and the aluminum hydride, or the aluminum tetrahydride. There's 4 hydrogens. There's a negative charge on the aluminum. This thing acts, so the ALH bond is very polar, almost ionic. Not quite, but almost, okay? These hydrogens act as hydrides. Hydride ion is H minus. That's the hydride ion, H minus. Hydride ions are very powerful nucleophiles and bases, okay? They're very unhappy. They want to get rid of that negative charge, and they want to do it by reacting with something that allows them to become less reactive, okay? So aluminum hydride acts like a source of hydride ions, and it reduces carbonyl compounds. Now, the reason you guys won't use this in the lab is it's so reactive, lithium aluminum hydride. If you have a little bit, it's a nice fine powder. If you have a little bit of powder and you spill some water in it, it catches fire. Okay, that's why we don't use it in the lab. And that's because it's very reactive. We have to have special conditions. We have to make sure that we're very dry conditions, no water around. And it will very rapidly reduce a carbonyl compound. And lithium aluminum hydride will reduce any of these reactions. Okay? So let's take a look at the mechanism. And we're going to just reduce acetone. Okay? And all that's going to happen is both of these electrons in the hydrogen aluminum bond are going to attack the carbonyl compound at the carbonyl carbon. And we're going to promote an electron up to here, and that gives us our what we call our tetrahedral intermediate. Okay? We do this under dry conditions. It gets a little complicated. What ends up happening, we now have aluminum trihydride, which is a neutral compound, and that can go on and do further reactions. Okay? Each molecule of lithium aluminum hydride can actually reduce 4 carbonyl compounds. These are still reactive. But this thing then, we have to, after the reaction is complete, we work it up. And we typically work it up. I'm going to get rid of this by adding a mild acid and H2O, and we end up getting our alcohol. Okay? Again, lithium aluminum hydride will reduce esters as well. Let's take a look at what happens when we reduce an ester with lithium aluminum hydride. Now I'm going to do things a little different, and this is what you might often see for a mechanism. Although we're using lithium aluminum hydride, it acts like H minus, and you may see sometimes people do something like this. So we have now, I'm going to do the methyl ester of just any generic compound. What you may see is this, just hydrogen, or hydride, okay? Just be aware. Typically I'm going to use, in the next step, you'll see what happens in the next step, I'll use aluminum tetrahydride. But this reacts and gives us this compound. We've added our hydride to the carbonyl carbon to form this tetrahedral intermediate. Now this thing can do something that's slightly different. We're going to see this particular mechanism a little bit later when we talk about esters specifically. This can actually eliminate a portion of the molecule. It's just going to, that negative charge is going to reform a carbon-oxygen double bond, and it's going to kick out this thing to give us an aldehyde and an alkoxide. Anion. Okay? But there's lots of lithium aluminum hydride around, and lithium aluminum hydride will reduce any carbonyl group. And what do we have? We have a carbonyl group. Okay? So this will just react with more. Again, I used hydride last time. This time I'm just going to use this. It's effectively adding hydride again, and we just get another reduction. And that gives us RCO minus HH, okay? And we're not going to worry about the rest of it. Now, both of these In the next step, we add a small amount of aqueous acid, and we end up getting our primary alcohol, plus in this case, methanol. The methanol gives us that. Sorry. Okay. Now, as it turns out, so the way we write these reactions, typically when we're talking about a synthesis, what you will see written on a piece of paper the reaction we just did, what we'll often see is, what did we use? We used R. This is telling us there's two steps in the reaction, okay? We have to do this reaction first. We have to let it go to completion, and then we add the water, and we end up getting for these particular reductions of esters, typically we're interested in this alcohol. Somehow we had some source of an acid, we made an ester, and then we reduce it to get this alcohol. This is a byproduct which we're probably not interested in, but it's easy to get rid of because this is probably some organic molecule very soluble in organic solvents. Methanol is a nice small alcohol that's very soluble in water. We can separate them at the end and get a pure alcohol. A similar reaction, so lithium aluminum hydride, very nucleophilic, it's also very basic. That's a common theme. Oftentimes good nucleophiles are good bases because both of them just need a pair of electrons. And in fact, a nucleophile reacting with an electrophile, that is really just a Lewis acid-base reaction. And then when we talk about base, we're talking about Bronsted acid-base reactions. So go back into your first year notes and take a look at Lewis acid-base reactions. Organic chemistry is full of Lewis acid-base reactions, but we typically talk about them as being nucleophiles reacting with electrophiles. We don't typically talk about Lewis acids and bases. We talk about electrophiles and nucleophiles. I told you that lithium aluminum hydride reacts violently with water, causes fires. It reduces all carbonyl groups. We have another milder, and I think in fact you guys will do one of these reductions. You did in the past. We have another compound that we can use to reduce carbonyl compounds. And that is sodium borohydride. Okay, this looks a lot, right? Take a look up at the periodic table. We see aluminum right below boron. They act a lot the same. As it turns out, this looks much the same. It's a sodium cation and a borohydride. Anion, okay? In this case, the BH bond has much more covalent character than the aluminum hydrogen bond, okay? And BH4 is a mild reducing agent. And in fact, it's so mild, we can do this reaction. We can do the reaction of sodium borohydride in water. It reacts with water, but it's a very slow reaction. The same thing, lithium aluminum hydride, we can't have any acidic, even slightly acidic hydrogens. With lithium aluminum hydride, you can't do the reaction in alcohol. But with sodium borohydride, you can use alcohol as solvent, because the reaction with lithium aluminum hydride reacts with any alcohol to give H2 gas and an alkoxide minus. This is vigorous and fast. Okay? The same thing happens with sodium borohydride. This same reaction. Is very slow. It's very slow. So we can do these reductions under slightly aqueous conditions, or even use alcohol as solvents. With lithium aluminum hydride, we have to use inert dry solvents with no OHs, no activated protons that can be. So, but the other thing about borohydride, it'll reduce aldehydes and ketones, but not esters. Or acids. So if we want to reduce an ester or an acid, we have to use lithium aluminum hydride. If we want to reduce a ketone or an aldehyde, we can use either lithium aluminum hydride or sodium borohydride. In our lab, the nice thing is sodium borohydride is a nice, safe, relatively safe, easy to use reagent. Lithium aluminum hydride you won't use until you're doing a research project or you're in 4th year. Before you have to have a lot of experience before you can use any of the more reactive reagents. Similarly, we can talk about these reactions. As it turns out, we typically just work them up slowly in water. We don't necessarily use we don't need the acid in this case. The reason we need to use slightly acidic water in the aluminum case is to get rid of all the aluminum salts. They become messy, and you need the extra acid just to get rid of that gunky aluminum. In this case, it works out okay. We don't junk it up with all these boron compounds, but you do with aluminum, and that's why you need the acidic conditions. You don't need acidic conditions here, and you just end up with a reduction. The mechanism is exactly the same. Also, sodium borohydride we can also think of as a source of hydride, okay? Whenever you hear something as a hydride, you should be thinking about H-. Remember that. Hydride is H-. And when we talk about a hydride, any kind of metal hydride, it's often a source of H-, okay? So we don't have H- free in solution. That's very difficult to make. But with the aluminum, it's very, very polar bond, very close, very much more ionic. With the boron hydrogen. It's less polar, but it's still a good source of nucleophilic hydrogen, hydride. Again, the mechanism is the same, whether it be sodium borohydride or lithium aluminum hydride, exactly the same mechanism. Okay, I was going to start talking about oxidation. We know we can oxidize alcohols to carbonyl compounds. Okay, if we have a primary alcohol, we can get aldehydes. Okay, and I'm going to put a little star here. I'm going to talk about this in just a second. We can oxidize primary alcohols to get aldehydes, and we can oxidize secondary alcohols to get ketones. Okay, don't forget the carbonyl compound, the carbonyl carbon bonded to a hydrogen, that's what makes something an aldehyde. Notice in a ketone there's no hydrogen on the carbonyl carbon. That's the difference between an aldehyde and a ketone. Secondary alcohols get oxidized to give us ketones. Tertiary alcohols are difficult to oxidize, and in fact when they do oxidize they don't give us anything useful, they just break apart, right? Because we have three groups on that carbon already, we can't fit a carbonyl there, right? Carbon can only have 4 bonds, right? That's something you should be telling yourself all the time when you're writing your midterms. Carbon likes to have 4 bonds, carbon likes to have 4 bonds. Whenever you draw a carbon with 5 bonds, you've drawn something wrong, or you're in an advanced inorganic class, okay? You should never see 5 bonds to carbon. If you see 3 bonds to carbon, we do have compounds that have 3 bonds to carbon, but they're going to be reactive, right? Carbocations just have 3 bonds, but they're reactive. They don't like to stick around. Tertiary alcohols cannot be oxidized because they're using up their valency. We can't form carbonyl compounds. Now, why did I put this in a star? Aldehydes and react with water, even small amounts of water, to form what we call hydrates. And this thing, it has a hydrogen on that carbon still. It's like a secondary alcohol now, right? And they can react further and be oxidized to give acids, okay? So if we want to oxidize a primary alcohol to an aldehyde, we have to be very careful and use very dry conditions. We have to use special reagents that do not have any water in them. If there's water, We quickly establish that equilibrium with the hydrate, and the hydrate reacts very rapidly with even mild oxidizing reagents to form the carboxylic acid. So primary alcohols quite often get completely oxidized to the carboxylic acids. Secondary alcohols, they also form hydrates, but their hydrates have another R group there. They don't have an H there. They're no longer, they're like tertiary alcohols, so they can't be further oxidized. We're almost done. I'm going to throw something up here quickly, just because I want to ask you. Does anybody see the clicker? Got it. There we go. Okay, so what you will notice, this will come up in just a second. I use the slides to keep me in the right place. Okay, there's the mechanisms. All these are in the slides, which I've posted on Acorn now. And one of the things I've done is stripped out all the animations in my portion of the slides. Your guys' isn't. What we're going to take a look at next time is, this is where we ended today. We're going to take a look at the common type of mechanism for oxidation. Then we're going to go through a number of oxidations, some of them quite complicated. And I will tell you when I think something's really complicated. In other words, you should know that's hard. That would be a hard question on an exam. And there may be hard questions, but there's going to be easy questions as well.